Welcome back to Unit 5, Video Lesson 4, Part 2. This part's optional unless you miss class. What we're going to talk about now is how the signal transduction actually occurs across the synapse. So how is that chemical signal generated? And for you to understand this, you need to first recall the electrical signal and how it was traveling down the axon of the neuron, which we discussed last day. So what happens is we have the electrical signal travels down the neuron from dendrite to axon. And it's traveling through the sodium-potassium channels like we discussed, and it gets to the presynaptic membrane, the axon terminal, where there are also voltage-gated calcium channels. And these channels open up and allow calcium ions, which are positive, to flow in. Ca2+. Ca2+ then binds to the synaptic vesicles and cause them to fuse with the plasma membrane. When they fuse with the plasma membrane, they release their contents with their neurotransmitters. The neurotransmitters then diffuse across the synaptic cleft and bind to a receptor on the other side. When they bind to this receptor, it opens and then allows ions into the postsynaptic membrane. And depending on whether those ions are positive or negative, they can influence whether or not an electrical signal is conducted along the next axon. Okay, so I kind of described it. Now we'll put it down here in details. So this is step 1. Okay, step 1 is electrical signal travels along axon to terminal, which is also called the presynaptic membrane. Where the blank millivolt charge causes the voltage-gated calcium channel to open. So the millivolts there, give you a second to think about it, it is the maximum voltage that can be reached. Recall that's plus 40 millivolts. Will actually open the calcium channel when it reaches the calcium channel. And because there's a high concentration of calcium outside the cell, step 2, look right here, is calcium rushes in to the cell. This then causes step 3. Okay, if we go back up, step 3 is a synaptic vesicle traveling to and fusing with the plasma membrane. So the calcium binds to vesicular proteins, that's proteins that are associated with the vesicle, such that the vesicle moves to and fuses with the presynaptic membrane. And this is really just a fancy case of what do we call it when vesicles fuse to the membrane to release things outside of the cell? He said exocytosis. You are correct. That then leads to step 4. If we suddenly release a bunch of neurotransmitters right here, the concentration is going to be really high, and naturally the neurotransmitters are going to do what across the synapse? Yes. So neurotransmitters are then released from the fused vesicle into the synaptic cleft. Where they diffuse across to this postsynaptic membrane. Once they reach the postsynaptic membrane, they can actually fuse specifically to a receptor. So 5 would be this right here. We're going to write this on the next page because it won't all fit on this page. The neurotransmitter NT binds to a specific receptor. So different neurotransmitters have different receptors, but they are all of the same class in that, well, they are actually all of the same class, but they're mostly of the same class. They are what we call ligand-gated ion channels. So we talked about voltage-gated ion channels. They open when a voltage change occurs. Ligand-gated opens when a ligand binds to them. A neurotransmitter is an example of a ligand. So the NT binds to a specific receptor and causes the receptor to open, allowing ions to flow across the membrane. Now, if these ions cause an increase in membrane potential, they are what we call excitatory. And can cause the electrical signal to resume in that neuron. So the electrical signal to be sent. If the neurotransmitter decreases membrane potential, opens a channel such that either negative ions are flowing in or positive ions are flowing out, it's called an inhibitory neurotransmitter. And it prevents the electrical signal from being sent. And then the last step of the chemical signal, to make sure that we can continue signaling, if we go all the way back up here, step 6, involves removing the neurotransmitter from the synapse. So the neurotransmitter is removed from the synaptic cleft. So that signal does not persist. And synapse can refire. Okay, so those are the 6 key steps to transmitting a chemical signal across the synapse. Now we're going to take a little closer look at what is the actual nature of the chemical signal, and specifically, what are neurotransmitters? And because we don't need to keep referring to the picture, we're going to zoom back in here. Let's get us back to 100%. There we go. So, in the simplest definition, neurotransmitters are chemicals that transmit signals across the synapses of the nervous system. Interestingly, some neurotransmitters are also hormones. So neurotransmitter functions just across the synaptic cleft. A hormone signals via blood to other areas of the body. And the example, a key example of this is epinephrine. So it can signal both between neurons and throughout the body. So there are some key neurotransmitters in our body. Now, neurotransmitters can be divided into 2 main classes. They can be inhibitory neurotransmitters these cause a decrease in the potential difference of the cell. and thus inhibit an electrical signal from being sent. Whereas we have excitatory neurotransmitters, which cause increase in potential difference in the cell. And thus encourage an electrical signal being sent. One of the complicated things about our nervous system is some neurotransmitters can be inhibitory in certain regions of our body and excitatory in different regions of our body. Perfect example is acetylcholine. It inhibits our heart rate but excites our skeletal muscles. So let's take a closer look at some of the key neurotransmitters in our body and the functions that they perform. The first one we're going to discuss is acetylcholine. Acetylcholine. Spell it out and try saying it. Okay, acetylcholine decreases heart rate. But increases skeletal muscle contractions. It's primarily associated with the parasympathetic response, and as well, deficiencies in acetylcholine which we abbreviate ACH, are associated with Alzheimer's disease, which is a form of dementia. Another key neurotransmitter that we discuss is epinephrine. Another key neurotransmitter that we discuss with respect Another key neurotransmitter that we discuss is norepinephrine. It acts counter to acetylcholine. It increases heart rate. And increases breathing rate. creates a sense of well-being. And is associated with the sympathetic response. And deficiencies in norepinephrine are often associated with depression. I don't know what I did there, but I definitely spelled deficiencies wrong. And while there's over 50 different neurotransmitters, there's two more I'd like to discuss because they're kind of key in addiction and moods, and that is dopamine, which along with epinephrine creates a sense of well-being. And is associated with, as was seen in the Teen Brain movie, associated with risk-reward pathways. And addiction. The other one is serotonin. Which influences our sleeping patterns, where excess serotonin equals excessive sleepiness. So those are 4 key neurotransmitters of our body. And as I said, while there's 50 of them, you can understand that how our nervous system is controlled is really quite complex, and the fact that some of these work in different areas of our body to be inhibitors and while in other areas they're excitatory explains why it's really difficult to treat things such as mental illness simply by treating them with things that influence neurotransmitters, because it's such a complex pathway. So before we move on, we just want to take a close look at what integration is. I've been using this term throughout this unit, and we just want to clearly define it. Integration is the summing up of all the chemical inputs at the postsynaptic membrane to determine if an electrical signal will be perpetuated. If after integration the potential difference of the cell is greater than blank, the electrical signal will be sent. What is the threshold potential? What does it have to reach? If you said negative 40 millivolts, you are correct. If it is less than negative 40 millivolts, the signal will not be sent. Clearly doesn't like me writing beside a picture here. Okay, so it will not be sent. So if we look at any given dendrite, there's a lot of axons feeding into it. So this picture is just showing some of the axon terminals feeding into it are positive, some are negative, and if we add it all up, we'll determine whether we have an excitatory response or an inhibitory response. So that's just considering all the inputs at the postsynaptic membrane. And this allows for greater control of the electrical impulse. It gives us breakpoints where we can stop that electrical signal if it's not the appropriate impulse. So it allows us to control and stop the all or nothing electrical impulse or electrical signal if it is inappropriate. Now, if we want to be able to reset a nerve pathway, we need to be able to remove neurotransmitters from the synaptic cleft. So NTs must be removed from the synaptic cleft in order to reset the nerve pathway. This can be done in one of three ways, the first being the least effective. Okay. First, we can simply wait for the neurotransmitter to diffuse out of the cleft. But this isn't really effective because one, it's slow, and two, you lose the neurotransmitter and it's not very controllable. Two, we can recycle the neurotransmitter back to where it came from. Which released it, the presynaptic cleft or the postsynaptic cleft? Or, sorry, membrane. Yes, back to the presynaptic membrane. via receptor-mediated endocytosis. So there will be a particular receptor on the presynaptic membrane that will bind to it. It'll form a vesicle around and bring it into the cell. As it does that, it lowers the concentration around the presynaptic side, encouraging the neurotransmitter to diffuse back towards that presynaptic side. And finally, we can actively destroy the neurotransmitter using enzymes typically released from the postsynaptic cleft. Postsynaptic membrane. Example, an enzyme called acetylcholine esterase. Just one E. So what this does, if we were looking at a neurotransmitter like acetylcholine, which decreases heart rate, acetylcholine esterase is an enzyme. I like to draw it like a Pac-Man. It comes along and munches up and destroys the acetylcholine. Okay, so if its job is to destroy acetylcholine, what's its effect going to be on the heart rate? If you said it increases the heart rate, you would be correct. Okay, because what we essentially did is decreasing heart rate is a negative effect, destroying acetylcholine is a negative effect, and a negative times a negative equals a positive to increase the heart rate. And we can always consider biochemical pathways this way. It's simple math. If you have 2 negatives in a row, you're going to get a positive. If you have 3 negatives in a row, you're going to get a negative effect. And by positive and negative, I don't mean whether it hurts or harms the body. It's just whether or not it increases a response or decreases a response. In this case, the negative ends up with a positive, increasing the response of heart rate. This is important when we're considering the action of drugs on the nervous system. There's many ways that drugs can affect the nervous system, but generally influence the actions of neurotransmitters or their receptors. So here are some different ways that drugs can influence the nervous system. 1. They can mimic a neurotransmitter. By binding to a receptor and activating it, causing it to react however it normally would to the neurotransmitter. They can mimic NT structure, but block its function. By binding to the NT's receptor, but preventing a signal or preventing activation. They can block NT destruction or reuptake such that signal is prolonged. They can block NT release such that signal does not occur. They can encourage overproduction or over-release of NT such that signal occurs more frequently than often. More frequently than normal, I should say, not than often. Some specific examples of this are, for example, cocaine, which blocks dopamine uptake, which prolongs the effects of dopamine, which leads to a sense of euphoria. There's also things like serotonin, reuptake inhibitors, these are a form of antidepressants because often when you are depressed, your sleep patterns are altered. And this helps to regulate sleep patterns. And it's also associated with mood elevation. There's also things like Valium, which enhances GABA, which is a particular type of neurotransmitter, binding to its receptor. And this helps to decrease anxiety. There's many others that can influence moods, some prescription, some recreational, but at the end of the day, anything that's influencing neurotransmitter activity is going to have a wide-ranging effect in our body just because of the complexity of neurotransmitters. So if you're interested in any particular type of drug, please feel free to come ask me how they work in your body, and I'll do my best to give you an answer. If you have any other questions about the chemical signal as well, come see me. Otherwise, I hope you have a good day, and I'll see you in class.